Yes, hello. Good afternoon, ladies and gentlemen. The last presentation of the day. I'm Khalid Hussein. I will be talking about J3-Series, our latest product for e-mobility from Mitsubishi Electric. And it is a scalable, high-power density silicon and silicon carbide module. In the talk, I will try to cover the following points, that the development concepts and lineup behind this new series, the chip technologies and features we are using, packaging technology and the performance of the module, and the rising prospects of. The first item, before I start, kind of an introduction, because I hear many questions. People are not aware of that Mitsubishi is providing chips as well as packages from the inside the same house. And we want, through this know-how, I really don't know if I should stop because of the announcement. Maybe it's better. Then it gives us time. You can read a little bit, make my life easier. Yeah. So. Okay, back to power semiconductor. So yeah, we would like to secure mature solutions for e-mobility, which is a very important and crucial factor. There are several points that needs to be addressed on the chip side as well as on the package side. And we have the capability of doing this under the same roof, give us the opportunity to optimize the solution. For example, being in the silicon or the silicon carbide, always we want to have efficient devices and addressing different applications, of course. Operation temperature, for example, in case of silicon carbide. Durability and ruggedness is essential. You're talking about lifetime of a car exceeding 10, 15 years and so on. The packaging, always size and weight matters. Scalability is a crucial factor. It gives you the flexibility of using the same footprint, for example, to address different car models, different capabilities. Longer life, we cannot say it more. Durability and reducing the stresses in the structure and being able to withstand the thermal stress. Functionality, the more we can integrate inside, the better the design and the easier it will be. So all these under the same roof, we leverage it to optimize the design of for automotive cars. And it's an ongoing, of course, activity, and it's always getting more and more out of the devices. In the history, we have been addressing different packages along the way. We started very early from 1997. We have what we call the case type modules. And then we progressed along the way with different solutions from Mitsubishi Electric for e-mobility. And most of the initial products were customized ones. And as you can see, we were always pushing for innovative solutions. You always find that we came up with something in a pioneering position, and it proved to be successful, and we move on to the next and to the next one, and improving always. And this is, of course, it's an ongoing process. It will continue. Now, our latest J3-Series. This is a transfer mold power module and direct cooled assemblies. This is what I will be explaining to you now, and then we will go further. The concept of the J3-Series, it's a very compact, what we call core module. It's like the first building block for us to make the inverters. And it's highly reliable of the transfer mold structure and very compact. It's a half bridge. We have two switches inside. It's half bridge configuration. When you have three of them, then you have the full inverter. Here we have the Hexa S. This is a smaller brother of the series, and the Hexa L, which is doubling. It uses 2 modules, and also this has been optimized in the layout like a mirror and a typical configuration to reduce the inductance. And here you can go all to 250 kilowatt plus level. You can go to 300 kilowatt depending on the inverter conditions. So then I will go through the lineup and some of the features. I won't talk about all the details, but you can get the idea, and then you can also see it in the booth. The J3 have silicon carbide as well as silicon in the same packages. Yeah? And here, this is the first one, Hexa S. It's a silicon carbide. It's you can see here the full bridge, 3 half bridges. The ratings breakdown voltage is 1300 volt, and the current, the peak current is about 350 amp. The RDS on about 3.08 milliohm for this one, and the features is written as written here. Efficiency is the key for the silicon carbide trench. We are using integrated temperature sensor. This is one of the features which is proved to be very valuable through the years for automotive modules. And then we have the SCM terminal. This is for short circuit protection. I explain it later on when we talk about the chip technology. The dimensions, as you see here, this is about 87 by 111. It's extremely compact overall. And with this, you can go up to kind of 120 plus kilowatt, or even 125, maybe with the conditions, you can go up to 150. So the next one, we go to the Hexa L. Probably now you got the idea of scaling up in a modular way using the same building block. Now we move to the Hexa L with 700 amp peak. The RDS on will be now about 1.54 milliohm. And dimensions, the length is slightly more than the Hexa S. It is now 193, but this is still within, it's less than 20 centimeters. So it's a very compact package, and it's proved to have very high power density for the application. Now, going to the other side of the story, this is the silicon part. And here we are using RC-IGBT. That is the reverse conducting IGBT. So it is always a solution similar to the silicon carbide. We all use the chip with the body diode inside. So now with silicon also, we are using one chip to do the function of the IGBT as well as the diode. It's a reverse conducting one. Here, this is 750 volt breakdown voltage at minus 40 degree. And you can already tell this is kind of focusing on 400 volt battery class of cars. The silicon carbide, on the other hand, is for the 800 volt plus, even 900 volt. It can be addressed with the silicon carbide from our side. Here, differences, also the efficiency is always there. We have integrated on chip temperature sensor and current sensor. And this is a technology that Mitsubishi have been using since right from the beginning. Over 20 years ago, we did this in automotive, and we keep on doing it because the feedback is always very positive about it. The bigger power out of the RC-IGBT, here we have it now 800 amp in the Hexa L, and this, it can go to about, more than about 180, 160 kilowatt range. It can go all to 200 if the conditions are matching. The sensors and so on are on the chip. This I will cover more details when we talk about the chip technology. Now, moving into the chip and the integrated features inside, I will split this into two. First, we talk about the silicon carbide, and then here you have that this is we're using our trench in-house developed chips over the silicon carbide, and we do have proprietary features we have here. For example, the tilted ion implant technology, And then you have the grounded, the bottom P well. This is also positively affecting, directly related to the stability of the device and the reliability of it for the gate and so on. The JFET doping to have much better RDS on value. And here we have a quick comparison showing that this is, we got like a 50% better than planar. We do have both technologies in-house. We have the planar as well as the trench. And this is something we have been doing it. And details about this are already available in published papers. And you probably you aware of it already, or you can go through it again. As integrated now, this is more specific details about the new J3. And this content, it will be presented in a paper tomorrow. We have a paper with details. My colleague will present it to Kurosaki-san. He will present this paper, and you can see some. Here inside, this is a conventional structure of transfer mold, for example, half bridge. Here in our new one, you can see we are integrating more. This is always something we have been doing, integrating more and more functionality with the power module. And here we can see we integrated the desaturation diode. It is inside the package. We integrated the temperature sensor and balance resistor, and as well as a terminal to enable better short circuit design support and capability. This will come later in more details. The key point, the new feature we are doing here, we are integrating these functions in a chip separate from the main silicon carbide chips. So this is what we call a multi-function chip. And the multifunctional chip have already the desat diode, the temperature diode, and the terminal for short circuit protection. And with the help of this multifunction chip, we could achieve higher power density because we could reduce the size of the package. And also not using the active area of the silicon carbide to sense the temperature. So we're sensing it separately, and this is achieving higher power density. Also, internal inductance can be reduced because of the overall size reduction. The layout itself can be optimized in a better way. And then the short circuit, it will be clear in a second. Here, this is, for example, the internal inductance. It can be reduced by 20% by the help of this optimized layout and functionality. Another important feature from the multifunction chip, this is the temperature sensing. And we are doing it with the diode. We don't use thermistors. And clear, if you look at this, you can see immediately the advantage. With the diode, you have better response. You have better linearity in the output. You can predict the temperature more easily and higher accuracy with this. The third feature, this is with the short circuit protection. And this also, we do have another paper. Tomorrow you will see this in the poster session. My colleague Samura-san, he will present this. So you can have more details there in that paper. So what we are doing here, by enabling access to the this is what we call SCM. This is like the short circuit monitor, plus the desaturation diode. So these two together can help make the protection very rapid, very fast. And this is very key question for silicon carbide, because always you have the trade-off. You want to make the best out of silicon carbide in your gate voltage, gate control, but you have to be ready for short circuit to be able to stop it on time. And here we can see the amount of, we could reduce the energy, the stress during a short circuit event. Yeah? So a very simple comparison, you can see it's already 70% reduced. So that is less stress, means longer lifetime of the product, longer lifetime of the module and the car at the end of the day. So this is also something included already for the silicon carbide. Now, I move to the silicon part. It's the same package, two solutions. With the silicon, now we are using reverse conducting IGBT, which is simply combining these two devices in one device. And you could see already, oh, there's advantage that you have less, more compact size, less parts to assemble, one step less, and so on. So this is always going in a good direction. Of course, this is just image of what the chip should, it's not exactly what it looks like. If we look at also reverse conducting IGBTs, there are different types of reverse conducting IGBTs. And usually the main concern is, oh, is it okay? Is it efficient? How about the control of the diode? Do I need to do something? There are different approaches. And the approach we are using is to make sure you have a very good trade-off in the characteristics. And if you, with some competition comparison here, clearly we have, and you can get the merits of a smaller total size, high current density, lower temperature swing, helps you in the power cycling. And then further on, we want to move into 12-inch. And this is immediately, it calculates back in the, the capacity improvements, the productivity, and so on. So this is all in making the same story. Other technologies integrated in the RC-IGBT. This is something we have been doing, as I said, more than 20 years now for automotive. And it is in actual cars running. And so we do the same for the RC-IGBT. We have a temperature sensor on the chip itself with a very good linearity. And you have a current sensor with a current mirror for protection. This also helps very in the short circuit protection. You can be rapidly control it. And not only short circuit, you can define over current level or short circuit. So this gives you more and more design flexibility. Now, packaging side, moved from the chip to the package, and then I show you a little bit of it. Here, this is, we are comparing with our previous generation of TPMs, transfer mold power modules, and the new J3 TPM, we solder our modules to the pinfin structure, or it can be soldered directly on the design, the end inverter unit of the car. And because you have better thermal interface through the solder, immediately you have improvement in the RTH value. Also, you don't need the springs to mount the TPM, and it gives you this reduction here of almost like about 30% better RTH. Another important feature which Mitsubishi have been using since 2001, already 23 years ago, we got rid of the wire bonds, aluminum wire bonds on the chip. This is not good, this is a no-go. So we are using direct lead bonding. Immediately you can see you have much better power cycling capability. You have a better reduced strain inductance, the uniform temperature distribution. And you can see from this simulation results, you can see here the temperature is also lower and more uniform. And this is again less stress, again longer lifetime. Also, it have a safe conduct on fail capability. This is in case of the, if you want to have an active short circuit in the motor, then this is give you a safety added on feature. And they have also already published some papers about this. It is also available in the media. Then approaching the end, this is the how to check the performance with such a compact package. If initial or early evaluation would need support definitely. And we make an evaluation kit, and this is here. We have it on the booth. Please come and have a look. You can, it's assembled in a cooling jacket, and to enable the early evaluation of the product before going on to the actual or the series design. Performance-wise, this is also from, you can find it in the paper. And here we some simulation under these conditions. You can see here clearly from the Hexa L, for example, you can get more than 500 ohm RMS at 10 kilohertz. And as we said, with such dimensions, you can get this power immediately. You can appreciate, oh, okay, there's a good power density here from a short or for a very small footprint. The Hexa S, similarly, this simulation is done with silicon carbide and for aluminum pinfin. Now we have also copper pinfin good for us, and this is our priority now. We're going ahead with the copper. If with aluminum we can achieve this, then you can imagine also with copper you have a better capability to do this. And to conclude, I would just start rising prospects of e-mobility or automotive, other modules. This J3, it is an evolution, part of the evolution of Mitsubishi offerings for e-mobility. We had a lot of modules along these since 97. We are now entering the 27th year. And the know-how and we got out of this. Now we put in our J3, and the track record we achieved so far, we could achieve more than 29 million vehicles using Mitsubishi modules for traction. And this is until the end of last year, 23. And so we are confident, we feel we are very proud of this record, and we are using or making is linked to this new development. And of course, it's one step, we would say. It's a step forward to realize the e-mobility expansion in a scalable way. So we don't want to be, limited by, this is too much power, this is less power. We make it scalable. You can adjust. You can go ahead with it. So that is all. Please come and visit our booth. I'm not sure if I exceeded the time, but yeah. So thank you very much for your attention, and we are available. And here's the contacts. Please let me know if you have anything I can do. Thank you.